Right now, about 65 billion particles of something are passing through every square centimeter of your body, every single second. They're going through your walls, through the floor, through the entire planet like it's not even there. We've known about them for 90 years. We spent billions of dollars trying to catch just one. We built detectors in abandoned gold mines. We cooled tanks of liquid xenon to absurd temperatures. We waited and waited. And the score so far? Zero. Not a single one. Tonight on Stardrift FM, the story of how humanity picked a fight with 85% of the universe and is losing badly. So here's the situation. Everything you've ever seen, everything you've ever touched, every star, every planet, every galaxy, your dog, your breakfast, every atom on the periodic table, all of that adds up to about 5% of the universe. 5, that's it. You know that feeling when you check your bank account and 95% of the transactions are labeled unknown? That's cosmology right now. The other 95% breaks down like this. About 27% is dark matter, invisible mass that holds galaxies together but doesn't emit, absorb, or reflect any light. It's not antimatter that produces detectable gamma rays when it meets regular matter. It's not black holes. Microlensing surveys have ruled that out. It's something else entirely. Something that interacts with gravity but is otherwise completely invisible to every instrument we've ever built. And about 68% is dark energy, a mysterious force or property of space or something that's pushing the entire universe apart and speeding up. Not concentrated in any one place, just everywhere, uniformly filling every cubic meter of space. We don't know what either of them are. Dark matter makes up 85% of all mass in the universe. It's everywhere. It was here before us. And after 90 years of searching, we have absolutely no idea what it's made of. This is the scorecard, humanity versus dark matter. We'll be updating it as we go. Right now, the game hasn't started yet, but trust me, it gets ugly fast. What we're going to do tonight is walk through this whole saga. From the guy who discovered dark matter in 1933 and got laughed at for 40 years, to the woman who proved it and never got a Nobel, to the $2 billion detectors buried underground that have found exactly nothing, to the biggest galaxy survey ever built, telling us that maybe, just maybe, everything we thought we knew about how the universe ends is wrong. It's a story of spectacular failure, and it's way more entertaining than it has any right to be. 1933, a Swiss-American astronomer named Fritz Zwicky is staring at a cluster of galaxies called the Coma Cluster, about 1,000 galaxies, all gravitationally bound together, orbiting their common center of mass like a swarm of bees around a hive. And Zwicky notices something that doesn't add up. The galaxies are moving way too fast, like assuredly too fast. See, if you know how much visible matter is in a cluster, the stars, the gas, you can calculate how fast the galaxy should be moving. It's basic gravity. More mass, more pull, faster orbits. Think of it like a merry-go-round. If you know how heavy it is, you know how fast the seats can spin before they fly off. Zwicky does the math, and the galaxies are spinning so fast they should be flying apart. The cluster should have ripped itself to pieces ages ago, but it hasn't. It's just sitting there, perfectly happy, held together by something. Zwicky calculates that the cluster needs about 400 times more mass than what's visible. 400 times! Let that sink in. If you were looking at a swimming pool and the waves told you there should be 400 Olympic pools worth of water somewhere nearby, but you could only see one, you'd have questions. Zwicky had questions. He calls this missing mass Dunkel Materie, German for dark matter. He publishes his findings, and the scientific community collectively says, yeah, no, and then moves on for 40 years. Now, to be fair, Zwicky was famously difficult to work with, and by difficult, I mean he once called his colleagues at Caltech spherical bastards because, as he explained, they were equally terrible no matter which angle you looked at them from. He also coined the word supernova, predicted neutron stars, and pioneered gravitational lensing. The man was simultaneously one of the most brilliant and most abrasive scientists of the 20th century. So when he said 85% of everything was missing, people found it easier to ignore him than to deal with him. But imagine that for a second. Discovering that most of the universe is invisible, publishing it in a major journal, and having everyone just go about their day, grab a coffee, write papers about other things. 40 years. The greatest missing mass mystery in the history of science, and nobody cared. Humanity 0, dark matter 1. Dark matter had been there the entire time. We just didn't believe the one guy who noticed. And here's the tragic part. Zwicky passed away in 1974, just a few years before the scientific community finally came around. He never got to see vindication. He was right about dark matter, right about supernovae, right about neutron stars, right about gravitational lensing, and the world told him he was wrong about all of it. Until it was too late. Now here's where it gets interesting. Fast forward to the 1970s. An astronomer named Vera Rubin, working with instrument maker Kent Ford at the Carnegie Institution, starts measuring something deceptively simple: how fast stars orbit inside spiral galaxies. Here's how gravity should work. Stars near the center of a galaxy, where most of the visible mass is concentrated, should orbit fast. Stars at the edge, far from the center, should orbit slower. It's the same reason Mercury zips around the sun while Neptune takes its sweet time. The farther out you go, the weaker the pull, the slower the orbit. This isn't complicated. It's Newton. It's textbook stuff. It should work everywhere in the universe. But that's not what Rubin found. Not even close. Stars at the edge of galaxies were orbiting just as fast as stars near the center. Every galaxy she looked at, same thing. Flat rotation curves across the board. The outer stars were moving at speeds that should have flung them into intergalactic space, but they stayed put. Something unseen was holding them in. Using Ford's custom-built spectrograph, a new instrument sensitive enough to measure the faint light of distant stars, Rubin systematically worked through galaxy after galaxy. In 1980, she published data on 21 spiral galaxies. All of them showed the same impossible pattern. The implication was staggering. Every single galaxy must be sitting inside a massive, invisible halo of something. Something with enormous gravitational pull. Something that outweighed the visible stars 5-1. Something you can't see. It only took 47 years and a completely different scientist proving the same thing for the world to go. Oh wait, Zwicky was right. Now think about what this means. Without dark matter, galaxies can't hold together. The Milky Way, gone. Stars at the edges fly off into the void, one by one, like passengers thrown from a carousel spinning too fast. No stable galaxy means no stable solar system, no sun, no Earth, no us. We're here right now, listening to this because something invisible is holding everything in place. Rubin proved this. The next generation dark matter observatory in Chile, the Vera C. Rubin Observatory, is named after her. Humanity 0, dark matter 2. We proved it exists. Still can't say what it is. 2006, 2 galaxy clusters, each containing hundreds of galaxies and vast clouds of hot gas, smash into each other at millions of kilometers per hour. The collision happened about 150 million years ago, and the light has just reached us. This is called the Bullet Cluster, officially cataloged as 1E0657-56. And what happened next is, to this day, the single most dramatic piece of evidence for dark matter ever recorded. Here's what we saw. The hot gas, which makes up most of the ordinary matter in galaxy clusters and is visible in X-rays, shown in pink in the famous composite image, collided. Gas hits gas. Electromagnetic forces kick in. Friction, drag, pressure. The gas slows down, heats up, and piles up in the middle. That's exactly what you'd expect, normal matter behaving normally. But the mass didn't stop. Gravitational lensing, the way massive objects warp space and bend light from galaxies behind them, showed that the majority of the mass in both clusters kept going. It passed straight through the collision like two swarms of ghosts crossing through each other. The mass separated from the visible matter. You could see exactly where it went, mapped out in blue on that composite image. The pink stopped. The blue kept walking. This is like watching someone's shadow walk away from their body. You know something is there. You can see the footprints. You can trace the path. But when you reach out to grab it, nothing. Just empty space that happens to bend starlight. And here's the kicker. The James Webb Space Telescope pierced the bullet cluster again recently and produced the most refined mass measurement yet. It confirmed everything. The dark matter is right there. We can see what it does. We can map where it goes. We just can't touch it. In January 2026, JWST also produced the most detailed dark matter map ever, using gravitational lensing across the Samos field, with 10 times more galaxies than any ground-based map before it, published in Nature Astronomy. Euclid has also been finding strong gravitational lenses at an astonishing rate. Over 500 candidates in its first data release alone, and it's only 14% done. By mission end, they expect 100,000. We are getting specularly good at seeing where dark matter is. We can map it across billions of light years. We can weigh it to decimal places. We can trace its influence from the first few 100,000 years of cosmic history to the present day. We're just no closer to knowing what it is. Humanity 0, dark matter 3. We literally photographed where it went. Still nothing in our hands. Let's take a step back, way back. 380,000 years after the Big Bang, the universe has cooled just enough for atoms to form for the first time. Before this moment, the cosmos was a blinding fog. Photons bouncing off free electrons, unable to travel more than a short distance in any direction. Then the electrons and protons combined into hydrogen atoms, and suddenly, light was free. It streamed out in every direction. And that light, stretched and cooled over 13.8 billion years, is still here. We can see it. It fills the sky in every direction. It's called the Cosmic Microwave Background, or CMB, the baby photo of the entire universe. Now, this baby photo isn't just pretty. It's a fingerprint. Those tiny temperature differences encode what the universe is made of. And the pattern in the baby photo only works if you add dark matter to the math. Without it, the picture looks wrong. The peaks are in the wrong places. The heights are off. The whole thing falls apart. Add dark matter and the simulation matches reality almost perfectly. It's one of the strongest pieces of evidence we have. Not just that dark matter exists, but that it was there from almost the very beginning. The Planck satellite, launched by ESA, measured this fingerprint with extraordinary precision in 2013. The result, 4.9% ordinary matter, 26.8% dark matter, 68.3% dark matter, 68.3% dark energy, not roughly. Prexlice, to a decimal point. We weighed the invisible. We know it's 26.8%, not 26.7, not 26.9. We measured it to 0.1%, and we still don't know what it is. That is the most cosmology thing I have ever heard. But here's what really gets me. Dark matter was here first. After the Big Bang, ordinary matter was too hot to clump. Photons kept blasting it apart. But dark matter doesn't interact with light. So while ordinary matter was stuck in its radiation bath, dark matter quietly built the gravitational scaffolding. The cosmic web of filaments and voids. Once the universe cooled, ordinary matter fell into those gravity wells like water flowing into valleys already carved by an invisible river. Without that scaffolding, there are no galaxies, no stars, no planets, no us. And right now, the Milky Way is embedded in a massive dark matter halo that outweighs all its stars 5-1. We are swimming in it. We always have been. That's either beautiful or terrifying depending on how much coffee you've had. Humanity 0, dark matter 4. We waited, mapped it, dated it. Still can't name it. But wait, because dark matter is only part of the problem. 1998. Two rival teams of astronomers are measuring distant Type 1a supernovae, stellar explosions that all go off at roughly the same peak brightness, which makes them perfect cosmic distance markers. If you know how bright something should be, and you measure how bright it looks, you can figure out how far away it is. Like seeing a streetlight at a distance. You know how bright streetlights are, so if it looks dim, it's far away. Both teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Supernova Search Team, led by Brian Schmidt and Adam Rice, are trying to figure out how fast the expansion of the universe is slowing down. Because obviously it should be slowing down. Gravity pulls things together. The Big Bang flung everything outward. Gravity should be putting on the brakes. The only question was how hard the brakes were being applied. Both teams find the opposite. The expansion is speeding up. The universe is accelerating. Every distant supernova is about 25% dimmer than it should be, meaning farther away than predicted. Something is pushing everything apart, and it's winning against gravity. Imagine dropping a ball, and instead of falling, it flies upward. Faster and faster. No parachute, no jet engine. It just goes up. And the higher it gets, the faster it accelerates. That's what the universe is doing. And nobody has the faintest idea why. Nobody saw this coming. I mean, nobody. Not theorists, not observers, not anyone. Both teams expected deceleration. Both were so sure the universe was slowing down that when the data said otherwise, each team assumed they had made a mistake. They spent months rechecking. They looked for errors in calibration, in the supernova data, in the distance calculations. There were no errors. Both teams independently, reluctantly, published the same conclusion. And in 2011, Perlmutter, Rice, and Schmidt shared the Nobel Prize in Physics for discovering something nobody wanted to find. This mysterious accelerating force got a name: dark energy. Coined by cosmologist Michael Turner in 1998, it makes up 68% of everything. It's not concentrated anywhere, it's spread uniformly through all of space, every cubic meter getting the same dose. And its nature is, if anything, even more mysterious than dark matters. At least dark matter acts like stuff. It has mass, it clumps, it bends light. Dark energy just pushes everywhere, all the time, and it's winning. About 5 billion years ago, dark energy overtook gravity's pull. That was the tipping point. From that moment on, the universe only gets lonelier. Distant galaxies are being pushed beyond our observable horizon, one by one, forever. The observable universe is shrinking, not because it's getting smaller, but because things inside it are being pushed out faster than their light can reach us. A treadmill that keeps speeding up. You're running, but the exit keeps getting farther away. So now we don't know what 27% is, and we don't know what 68% is. We're at 95% unknown. We are the 5%. Everything humanity has ever studied in physics, chemistry, biology, the entire periodic table, every element, every molecule, every grain of sand and drop of ocean is the rounding error of the cosmos. The universe looked at us and said, "You're a side effect." And then it kept going about its business, which apparently involves being 95% mysterious. Humanity 0, dark matter 5, and dark energy just joined the other team. Now here's where it gets really interesting. Enter DESI, the Dark Energy Spectroscopic Instrument. Mounted on a 4-meter telescope in Arizona, it has 5,000 tiny robotic fiber optic positioners that can each lock onto a different galaxy simultaneously. Imagine 5,000 tiny robotic fingers, each pointing at a different galaxy across the sky, gathering light at the same time. It has mapped 14 million galaxies and 800,000 quasars across 11 billion years of cosmic history. It is, by a wide margin, the largest three-dimensional map of the universe ever created. DESI uses a cosmic ruler, a preferred spacing between galaxies, about 490 million light-years, left over from sound waves in the early universe. Measure that spacing at different distances and you can track exactly how the expansion of the universe has changed over time. In 2024, DESI released its first results. And they were not what anyone expected. The data suggested that dark energy might not be constant. It might be changing over time. The statistical significance was 3.9 sigma, which translates to about 99.99% confidence. Not quite the gold standard of 5 sigma, but enough to make every cosmologist in the world sit up very straight in their chair. Then in March 2025, DESI released more data. The signal got stronger, 4.2 sigma, 99.995% confidence, still not 5. But the trend is unmistakable, and it keeps going in the same direction with every new batch of data. For 25 years, everyone assumed dark energy was just there, like a background hum, a constant. Einstein originally called it the cosmological constant lambda, a term he introduced to keep his equations balanced, then later called his biggest blunder when the universe turned out to be expanding. But after 1998, lambda was back, reinterpreted as the energy density of empty space itself. And for a quarter century, that was the story. Dark energy is a constant. The universe expands faster and faster forever. Case closed. Except now DESI is suggesting the background hum might have a melody. Dark energy might be evolving. It might be getting weaker. It might be a dynamic field. Something physicists call quintessence, named after the ancient Greek concept of a fifth element, the substance that fills the heavens. And here's a fun fact to keep you up at night. Quantum field theory predicts that the vacuum energy of empty space, the leading candidate for what dark energy actually is, should be 10 to the power of 120 times larger than what we actually observe. Let me say that again. The theoretical prediction is wrong by a factor of 1, followed by 120 zeros. That's not a rounding error. That's not even in the same universe as a rounding error. It has been called the worst prediction in the entire history of physics. And after all these decades, we still don't have a better one. Humanity 0, dark matter 6. Even the thing we thought was constant isn't. So what dark energy does next, whether it stays constant, gets stronger, or fades away, literally decides how the universe ends, not metaphorically, literally. The fate of every atom in existence depends on the behavior of something we can't see, can't touch, and can't explain. And right now, we have 3 options on the table. None of them are what you'd call cheerful. Option 1, the big freeze, also called heat entropy. This is the most likely scenario under current data. Dark energy stays constant. Expansion continues forever. Stars burn through their fuel and go dark, one by one, over trillions of years. Galaxies drift apart until each one is alone in an infinite void. The temperature of everything drops toward absolute zero. Black holes slowly evaporate through Hawking radiation over timescales so long they make the current age of the universe look like a blink. And then, nothing. The universe becomes cold, empty, and lifeless. Forever. No drama. No grand finale. Just an eternity of nothing happening. It's the most depressing option, which is probably why it's the most likely. Option 2, the big rip. This is what happens if dark energy gets stronger over time. What physicists call phantom energy, where the equation of state parameter W drops below -1. Right now, dark energy pushes galaxy clusters apart, but can't overcome gravity within a galaxy or a solar system or an atom. But if it keeps getting stronger, eventually it will. First, it tears apart galaxy clusters, then individual galaxies, then solar systems, then planets, then molecules, then atoms themselves. Everything gets torn apart, from the largest structures down to the subatomic. The earliest estimates put this at about 200 billion years from now. It's like the universe hitting the self-destruct sequence, but in excruciatingly slow motion. The last thing to go? The fabric of space-time itself. Even empty space gets torn apart. There's nowhere left to be because there's no more where. Now, I should mention, 200 billion years from now is a very long time. The universe is currently only 13.8 billion years old, so we've got a while. But a while is cold comfort when the mechanism is already in motion. That's like being told the building is on fire, but it's a really, really slow fire. Option 3, the Big Crunch. This is the comeback story. If dark energy weakens or reverses, then gravity eventually wins. Expansion slows, stops, and reverses. Everything falls back together. The universe collapses into a singularity. And maybe, it triggers another Big Bang. A cosmic reboot. The universe as a phoenix endlessly cycling through expansion and collapse. Some physicists find this poetic. Others find it terrifying. Most find it unlikely. Or at least, they used to. Here's the twist. DESI is suggesting dark energy might be weakening, which means the Big Crunch, an option that was basically off the table for 25 years, is suddenly back in play. One researcher put it bluntly, the new data seem to indicate the universe will end in a big crunch. Another called it potentially one of the most important results in cosmology of the last decades. So the question isn't just what is the universe made of? It's what happens when we can't figure it out in time. Humanity's 0, dark matter 7. It's not just invisible, it's also deciding the end game. And we don't even get a vote. Okay, so we know dark matter is real. We've seen its gravity, its shadows, its fingerprints in the oldest light in the universe. But what eye is it? What are the actual particles? What is this stuff made of? And this is where the story goes from fascinating to genuinely absurd. Because humanity has thrown everything it has at this question, and the answer so far is nothing. The leading candidate for decades has been WIMPs, weakly interacting massive particles. Heavy particles, maybe 10 to 1,000 times the mass of a proton, that interact via gravity and the weak nuclear force, but nothing else. They were elegant, theoretically motivated. They fell naturally out of supersymmetry models, and the math worked out beautifully. The predicted abundance of WIMPs matched the observed amount of dark matter so perfectly that physicists called it the WIMP miracle. There was just one problem. Nobody could find them. Enter the LZ experiment. Lucas Zeppelin, located 46,850 feet underground in the Sanford Underground Research Facility in South Dakota, a repurposed gold mine from the 1870s. It uses 10 tons of ultra-pure liquid xenon cooled to -100 degrees Celsius. The idea is beautifully simple. If a WIMP bumps into a xenon nucleus, it produces a tiny flash of light and a small electrical charge. The detector watches for those signals 24 hours a day, 7 days a week, month after month. They buried it underground to shield it from cosmic rays. They surrounded it with ultra-pure water to block stray radiation. They made the xenon itself the purest liquid in the world. Results after 417 days of watching, no WIMPs. 0. Not one candidate event that survived analysis. They set the world's most stringent limits on how strongly dark matter can interact with ordinary matter. And the answer is, if it interacts at all, it does so more weakly than anyone imagined. The allowed parameter space for WIMPs has been shrinking for decades. Every new experiment draws the net tighter. And so far, the net keeps coming up empty. But they did find something, accidentally. Solar neutrinos, boron-A neutrinos from nuclear reactions in the sun's core detected at 4 sigma significance, which is like building the most expensive fishing rod in history, casting it into the deepest ocean, waiting for over a year, catching nothing you were looking for, and reeling in a very confused tuna from a completely different ocean. They're planning to collect 1,000 days of data before shutting down in 2028. Hope springs eternal. It's not just LZ. Italy's Exxon ran the same kind of search underground at Gran Sasso. Same result, nothing. The ADMX experiment in Washington is hunting axions instead. ultralight particles that weren't even invented to explain dark matter but might anyway. So far, no signal there either. And then there are the wild cards, primordial black holes from the first moments after the Big Bang. Fuzzy dark matter, particles so light they behave like quantum waves stretching across entire galaxies. And in October 2025, JWST identified 4 objects in the early universe that might be supermassive dark stars, powered not by nuclear fusion, but by dark matter collisions in their cores. If confirmed, extraordinary. But might is doing an ENORM amount of heavy lifting in that sense. We have built the most sensitive instruments in human history, buried them in mountains and abandoned mines, filled them with the most expensive liquid on Earth, cooled them to temperatures colder than outer space, shielded them from every known source of interference, stared at them for years, and the universe's response has been, consistently, stubbornly, silence. Humanity 0, dark matter 8. Billions of dollars spent, not a single catch. At some point, you have to admire dark matter's commitment to staying hidden. It's the best hider in cosmic history. Now, here's where I need to tell you about the Rebel, because there's a theory out there that says dark matter doesn't exist at all, that we've just been doing the math wrong for 300 years. And the weirdest part, on the scale of individual galaxies, it works B-turn and dark matter does. 1983, an Israeli physicist named Mordechai Milgrom proposes something radical. What if Newton's laws of gravity just stopped working correctly at very low accelerations? Not wrong at human scales, not wrong for planets orbiting stars, but at the incredibly weak gravitational pulls you find at the outskirts of galaxies below a threshold of about 1.2 times 10 to the minus 10 meters per second squared, gravity behaves differently. It doesn't fade as quickly as Newton predicted. It stays stronger than expected. This is called MOND, Modified Newtonian Dynamics. And the thing about MOND that drives dark matter physicists a little bit crazy is that it works. On galaxy scales, MOND predicts rotation curves from visible matter alone. No invisible halos needed, no dark matter, no exotic particles. Just a small tweak to how gravity operates at very low accelerations. One guy changed one number in one equation and predicted galaxy behavior better than 40 years of dark matter models. The Tully-Fisher relation, the correlation between a galaxy's luminosity and its rotation speed, falls out of MOND naturally, while dark matter models have to be carefully tuned to reproduce it. That's either genius or the universe playing an elaborate joke on all of us. And here's what makes it even more maddening. MOND was proposed before most of the big dark matter detection experiments were even built. Milgrom has been sitting there for over 40 years going, guys, maybe you don't need to dig a gold mine. Maybe you just need different math. In 2024, new gravitational lensing measurements showed that galaxy rotation curves stay flat essentially forever, out to distances far beyond the visible edge of galaxies, where dark matter halos should be thinning out according to standard models, but apparently aren't. One team's conclusion was blunt. The obvious interpretation is that dark matter is a chimera. But here's the problem: the bullet cluster. Remember the ghost collision from earlier? Mass clearly separated from visible matter. Something invisible kept moving when the gas stopped. MOND can't explain that. If there's no dark matter, what was it that passed through? And the CMB. MOND can't reproduce those acoustic peaks we talked about. The baby photo of the universe requires dark matter in the math. Without it, the pattern is wrong. No version of MOND has been able to match the full CMB power spectrum. There's also the wide binary star test. Researchers at the University of St. Andrews looked at pairs of stars orbiting each other at very wide separations, exactly the regime where MOND should kick in. They found no deviation from Newtonian gravity. One called it a hammer blow for MOND, though MOND supporters dispute the analysis, arguing the data was processed incorrectly. The back and forth continues in journals and at conferences, with neither side backing down. In April 2025, there was a formal debate between Scott Doldson, defending dark matter, and Stacy McGaw defending MOND. The result? No winner. Neither theory explains everything. Both explain something the other can't. And scientists are still arguing about which something matters more. Dark matter's failure to show up in any detector keeps MOND alive. MOND's failure at cosmological scales keeps dark matter dominant. It's a stalemate. Humanity gets half a point, 0.5 to 8, because maybe, just maybe, we don't even need dark matter. The judges are still deliberating. And as if all of this weren't enough, there's one more wrinkle. It's called the Hubble tension, and it might be the crack that breaks the whole thing open. Two ways to measure how fast the universe is expanding. One uses the CMB, looking at the early universe just 380,000 years after the Big Bang, and gets a value of about 67.4 kilometers per second per megaparsec. That comes from the Planck satellite. The other method uses nearby stars, Cepheid variables, and type 1a supernovae in the local universe and gets about 73.0. That's the SH0S team, led by Adam Rees, the same guy who discovered dark energy. That's a 9% difference, way beyond measurement error. Both methods have been checked and rechecked and verified by independent teams around the world. Both seem right. Both can't be. Something is wrong with our understanding of the universe, and nobody knows what. Some physicists think the Hubble tension is the biggest clue we have, that whatever resolves it will also tell us something fundamental about dark energy, dark matter, or both. Others think it might just be a really stubborn systematic error that we haven't found yet. But it's been over a decade now, and the tension hasn't budged. If anything, it's gotten worse. Some physicists think resolving the Hubble tension requires new physics. Maybe there was a burst of dark energy shortly after the Big Bang, something called early dark energy, that would have changed the expansion rate in the early universe. Maybe dark matter and dark energy interact with each other in ways we haven't accounted for. A 2025 simulation from the Chinese Academy of Sciences explored exactly this. What happens when dark matter slowly converts into dark energy, or vice versa? The results showed measurable effects on how galaxy clusters align with the cosmic web. We might be able to test this soon. And that's the thing about the Hubble tension. It's not just a number disagreement. It's a potential window into entirely new physics. If the tension is real, if it's not a measurement problem, then something in our standard model of cosmology is missing or wrong. And given that our standard model already includes two things we can't explain, dark matter and dark energy, the idea that something else might be off is, well, it tracks. And here's the thing that keeps me going. We have more tools now than at any point in history. Euclid, ESA's Dark Universe Telescope, launched in July 2023 and is already mapping the three-dimensional distribution of dark matter across the sky. As of March 2025, it's about 14% done, 2,000 square degrees surveyed, with over 26 million galaxies observed and more than 500 strong gravitational lens candidates identified. By the time it finishes, it expects to find 100,000 strong lenses. First major cosmology results are expected in late 2026. The Vera Rubin Observatory, named after the woman who proved dark matter exists, is preparing to survey the entire visible southern sky with unprecedented depth and speed over and over for 10 years. It will track how the distribution of dark matter changes over cosmic time. If dark energy is evolving, Rubin will see it in how galaxy clustering shifts over the years. If dark matter behaves differently than predicted, Rubin will catch it. It's designed to see things we didn't know we should be looking for. XLZD, the next megadetector, will combine the technologies of LZ, X-Denant, and Darwin into one enormous next-generation instrument designed to push sensitivity to the very edge of what's physically possible, to what they call the neutrino floor, below which solar neutrinos become an irreducible background that you can't get rid of no matter how good your detector is. DESI keeps collecting data. Its next data release will cover even more of cosmic history. JWST keeps finding weird things. elongated galaxies, possible dark stars, impossibly early supermassive black holes that form too quickly for standard models to explain. Every year, the tools get better, the data gets sharper, and the questions get stranger. We have more telescopes, more data, more detectors, more computing power than at any point in human history, and we have never been more confused. And that, honestly, is the most exciting thing about all of this, because confusion, in science, means you're at the edge. It means the next discovery could change everything. We're living in what future textbooks will either call the golden age of cosmology or the era when everyone was wrong about everything. Either way, it's going to be a great chapter. Humanity 0.5, dark matter 8. But we've got reinforcements on the way. 90 years, billions of dollars, the most sensitive instruments ever built, and we still don't know what 85% of the universe is made of. But here's what we do know. Every failure narrowed the search. Every experiment that found nothing told us what dark matter isn't. The parameter space for WIMPs has been shrinking for decades. We're running out of places for them to hide. The Axion search is methodically working through its frequency range. And every new telescope, Euclid, Rubin, JWST, is mapping the invisible with more precision than the generation before. We know dark matter is there. We know how much there is. We know where it goes. We know it was here first. We know that without it, we wouldn't exist. We just don't know its name. And honestly, that might be the most remarkable fact in all of science. The thing we understand least is also the thing we need most. We're made of the 5%, the rare stuff, the cosmic exception. Everything we are, every galaxy, every star, every atom in your body exists because something we've never seen built a scaffolding first. And we've spent 90 years trying to find out what that something is, and we still can't. That's humbling, but it's also kind of wonderful, because it means the biggest discovery in the history of physics is still out there, waiting for someone to make it. The score is lopsided. Dark matter is winning, but we haven't quit. We're building bigger detectors, launching better telescopes, arguing about gravity at conferences, simulating the cosmic web on supercomputers. And one day, maybe, we'll catch that first particle. Or we'll find out gravity works differently than we thought. Or we'll discover something nobody has imagined yet, and the scoreboard will finally move. We've been at this for 90 years. What's another 10, or 20, or 50? The universe has been hiding this secret for 13.8 billion years. It can afford to be patient, but so can we. This is Stardrift FM. Keep drifting.